All right, everybody, so we're back again here. Now we're starting Module 11. So this is part 1 of your lecture series for this week. So today we're talking about the geological context for biological evolution. This is a fancy name for talking about Earth and what Earth is made of. We're talking about geology or rocks and the substance that makes up what we know as our home. And so our readings for this week include pages 198 through pages 218. So it's a pretty simple read for this Module 11, and so hopefully it's not too hard for you guys. I hope you're hanging in there and powering through. We have a few more weeks left of this academic semester, and then we're done for the year. I was just, these aren't new assignments, but these are assignments that are going to be due on April 21st. So these include our Module 10 quiz, so make sure you take that quiz. That was all about the universe, what we covered in Module 10 last week, or the astronomical context for biological evolution. So make sure you take that Module 10 quiz. And then also for our lab last week, we watched the Planetarium Universe video. So if you didn't watch that, you can still watch it. It's about 30 minutes long, and it is supposed to be played in the planetarium. However, since our laboratory planetarium trip got canceled, obviously due to our current circumstances, instead you just have to watch this video on YouTube for our lab, and everybody gets full credit. And then lastly, make sure you turn in your PowerPoint presentation. So I'm looking forward to those. I did already receive quite a handful, and so far they look really nice. So great job, guys. Hang in there, turn your PowerPoint presentations, and get points for it. So today we're doing Module 11, but I forgot to include a slide, but I will for the next lecture. But we're going to have 2 quizzes next week. So we're going to have quizzes over Module 11 and Module 12. Obviously, we had 2 weeks of spring break, and so that kind of pushed our class back about a week. And so we're going to try to squeeze Module 11 and 12 into 1 week. So you guys all have to take both quizzes 1 week from April 21st. So that would be April 28th. So make sure you guys pay attention to that on when those are due. You'll also have a lab for next week as well to turn in. It's the Stickleback lab. We'll be working on that this week. All right, so this is just a reminder, Module 11, you're reading pages 198 to 218. There are 3 sections for this module. They include Earth minerals, Earth's interior, and plate tectonics. So we're going to cover 2 of the sections today in lecture, and then we'll finish up with plate tectonics and anything else you need to know for the quiz. So let's go ahead and get started, and we'll knock this out. Okay, so you may remember this slide from last week's lecture. We started talking a little bit about Earth and how old Earth is. So we do know that Earth is approximately 4.6 billion years old. But why are we confident in this? And I mentioned last time, this is due to 2 things, our geological records and uniformitarianism. So basically, the same processes is occurring on Earth through time, and the processes that have occurred in the past are occurring even today. And so this is what most modern scientists believe in, is uniformitarianism. So keep that in mind. Also, looking back through all the geological records as well, through all of the different epochs, eras, and periods that we encountered through Earth's history. So when we look at our geological timeline here, we have several different eras and periods, and we have the age here listed in millions of years ago. And so we have the 3 eras that we know of, the Paleozoic, the Mesozoic, and the Cenozoic. And so several different periods have occurred in each of these eras. And our most recent era is towards the top, and our most ancient era is towards the bottom. And so you can see the Pleistocene period that occurred was approximately 1.5, 1.8 million years ago. The Cambrian period was approximately 570 million years ago. And so if you look at this chart here, we're really unable to determine the geological landforms prior to the Cambrian era. So that's all of the geological landforms that are found prior to 570 million years ago in the pre-Cambrian period. And so this is probably due to the fact that so many years have gone by, and it's just so old at this point in time. We're uncertain to what sort of geological landforms have occurred. Okay, so let's get into some basics. Now, hopefully this is a lot of review for everybody here, but let's talk about certain things that we do find on Earth's surface. So let's start off with some pretty basic concepts here. So the first concept that we want to talk about here are minerals. So we hear the term minerals. Obviously, this is not going to be like the type of mineral or type of, I guess, mineral that you're consuming technically in your body, like vitamins and minerals. But we're talking about rocks, minerals that exist on Earth's surface. So what is a mineral? So there are 5 different defining features for a mineral that make up a mineral itself. So these 5 particular defining features include the fact that a mineral is naturally occurring. The second defining feature is that a mineral is inorganic, so it was never alive. The third defining feature is that it is a solid. And the fourth defining feature is that it is a constant chemical composition throughout. And then lastly, a mineral needs to be in a crystalline structure. So these are the 5 components that define what a mineral actually is. And we see tons of different types of minerals that have occurred, through our geological records here. And this includes different types like olivine or quartz, just to name a few. But there are several different types that we will see. And one thing about minerals here is that silicon and oxygen are the 2 most abundant elements in Earth's crust. And so we know that silicon is a type of mineral, and they are classified in 2 different ways. And these 2 different ways include whether they are or they are not silicates. So are they silicates or are they non-silicates? So these silicates are basically a silicon-oxygen tetrahedral unit. And they can be isolated or joined together in a crystalline structure. And so if you look at this diagram above my box here, this shows you the abundant elements in Earth's crust only. These don't include the elements that make up the rest of Earth. If I had that diagram, that would include a lot of iron. And I didn't include it here because we will talk about it a little bit later here in my presentation. But iron makes up a lot of the actual Earth instead of just the Earth's crust. But you can see here, iron does make up a little bit of Earth's crust, but it makes up quite a bit more when we talk about the core of Earth as well. So oxygen, you can see here, is the primary element here in Earth's crust. It makes up almost 50%. And silicon makes up about 1/4 of Earth's crust. And then you have a handful of other different types of elements. And so Basically, just keep in mind that minerals can be classified whether or not they contain elements or not of silicone, or if they don't contain silicone or silicates. Okay, so we know what a mineral is now. So what is a rock? Now, you can't really use these interchangeably because they are different things. So elements are basically chemically combined to make minerals. Okay, so that's the basic structural building block. So elements like silicon, oxygen, iron, or whatever, those are chemically combined to make our minerals. Minerals are physically combined to make our rocks. So now, what is a rock? Well, obviously you see them, around your backyard or wherever. But the formal definition for a rock is an aggregation of one or more minerals and other materials that are brought together to create a cohesive solid. So these minerals, there can be more than one of them, and that will create a rock. So you'll see rocks that have several different types of minerals, a different mineral makeup depending on which rock you're looking at. These are just some examples here above me of different types of rocks we might see. And we'll talk a little bit more about some different categories of rocks that we have. And so hopefully this is a review for you again, but we're just going to touch on it in case, just to refresh your memory. So what different types of rocks are there? Well, we can classify our rocks into 3 different preliminary categories. And so the first category are our igneous rocks. The second category are our sedimentary rocks. And the third category here are our metamorphic rocks. And so we're going to go through each of them and talk about what makes up each different type of rock. And these are all found on Earth, obviously, but they're formed in different ways. So I mentioned our igneous rocks. So our igneous rocks are formed from a hot molten mass of melted rock materials. So any sort of magma or volcanic action that's happening. So this is where we're going to typically see our igneous rocks. So I just mentioned the word magma. So what is magma? So that is basically a mass of melted rock materials. It's pretty hot, it's molten, and eventually it will cool in order to form an igneous rock. We also see granite. Granite is a light-colored igneous rock. It's made up of a few different minerals, which include quartz, mica, and feldspar. And then we'll also see basalt, and basalt is a really, really dark and dense igneous rock, and the mineral grains are too tiny to see. And one really cool thing about igneous rocks is the size of the mineral grains. So depending on whether the mineral grains are really, really small or really, really large, depends on how fast or slow the magma or the molten mass has cooled. And so that will help classify igneous rocks. And if you guys ever take a geology class down the line, they'll typically will have a lab where you get to look at igneous rocks and classify different igneous rocks based on grain size. So, all right, so we also have our sedimentary rocks. So our sedimentary rocks here are basically formed from particles or dissolved materials from previously existing rock. So sediment is the root of the word sedimentary. And so when you have sediment, that is what our sedimentary rocks are formed from. And so sediment is basically an accumulation of either silt or clay or sand or any other really fine weathered materials that you might have. So small particles that have been weathered down over time and form sediment eventually can form sedimentary rock. And these are through 2 different avenues. And so when you have these sediments, you might see 2 different things that are happening. So the 2 processes you might see are compaction or cementation. And so when you see compaction, this is basically the reducing of a thickness. So you have a thick amount of sediment here, but it's the reducing of the thickness of sediment or sedimentary deposit through the packing of grains more tightly. And so the pressure is pushing down on that sediment and compacting it very, very, very tightly and leaving no space between any sort of grains that you might have. Now you also have cementation. So this is when the space that exists between the sediment that you have between either the clay or the silt or the sand. So all that space between all of those sediment particles are filled with a chemical deposit, and that could be a different type of sediment or some sort of other chemical deposit. So you basically have something that is cementing. If you think about, cementation in general, if you have like big cobble rocks and that you pour like a cement onto the cobble rocks, it will fill in all that spaces and then cement it into place. And so if you see a sedimentary rock, it would probably have smaller grains that are cemented in by like some sort of very homologous looking chemical substance. And one of the really cool ways to determine if you have a sedimentary rock, or one of the types of sedimentary rock, are sedimentary rock that contain fossils. So if you look at this image that I have here above me, you can see, if you look closely, that there are fossils within this sedimentary rock that have been cemented in and filled in by some sort of chemical deposit. But within that, there are shells and other fossils. So that's one of the fun ways to determine if you have a sedimentary rock. Now, not all sedimentary rock have that, but some of them do. Okay, and then we also here have our metamorphic rock. So our metamorphic rock is kind of our wild card of rocks. So this is basically any previously existing rock that you have that has been changed either by heat, pressure, or any sort of hot solution from one type of rock into a distinctly different type of rock. So you'll have basically a metamorphosis of rock, metamorphic rock, that's occurring from one type to another. And so these changes in this metamorphic rock can occur due to either movement of the crust of Earth, which we'll talk about what the crust is here in a few seconds, but we will talk about movement also in a next lecture, which is our plate tectonics. But anyway, I digress. So metamorphic rocks occur due to changes either in the movement of the crust or the heating of hot solutions from magma. And so when you either have pressure or heat that changes one type of rock to another over time, this is when we find our metamorphic rock. All right, and so one of the really cool things about our rocks here is that rocks change through time. And this is what we would call our rock cycle. And so obviously we have our three different types of rock: igneous, metamorphic, and sedimentary rock. And they change over time and become one or the other, or transform over time depending on what sort of process is happening. If we have cooling, if we have melting, if we have heat or pressure, weathering, erosion, and compaction or cementation. Any types of processes that we have will transform our rocks over time. And so we'll look in depth more at the next slide on what our rock cycle is. Okay, so we have, you can see here, our igneous rock, our sedimentary rock, and our metamorphic rock, right? And so this is our cycle that's occurring. And so we have our igneous rock. Let's start there in the upper left-hand corner. And so we can have weathering and erosion that occur of an igneous rock. And so if that happens in an igneous rock, then it can become sediment, which then can become sedimentary rock. If you remember, that's how sedimentary rock is formed. Also, igneous rock can also become metamorphic rock because it can change from one type to another over time, either through heat or pressure. And so our igneous rock can become either one of those. If we look at our sedimentary rock, that can become metamorphic rock through metamorphism, which can change through heat or pressure. Our sedimentary rock can also change back to sediment and then become sedimentary rock again, which is interesting because, I mean, obviously it can erode over time and become small particles and then become sedimentary rock. And that sediment becomes sedimentary rock through lithification or cementation or compaction. And then we also have our metamorphic rock here. And if our metamorphic rock undergoes weathering or erosion, it can also become sediment and then eventually become sedimentary rock. But our our metamorphic rock can also become magma. And then our magma can solidify and then become igneous rock. And so this is just basically showing you that all of our different types of rock classification can become something else if enough time has passed and through the elements that have occurred, either weathering, erosion, cementation, compaction, heating, cooling, solidification, melting, whatever process that exists in certain parts of the world can help allow the different processes to occur and have different rocks become one another over time. Okay, so let's talk a little bit about Earth's interior. So one thing that we do know is that Earth is not solid. I mean, even though when we go about our day here on Earth's surface, and over time, you know, our interactions with the environment, we might think that Earth itself is solid, but it actually is not. We do have waves that are occurring within Earth, and these are called our seismic waves. And so what seismic waves are is they are sudden movement of large sections of rock. And these movements produce our vibrations that can move as waves throughout the entire Earth. So start thinking of like a good example that you guys might see are earthquakes, right? So earthquakes happen and you can see sudden movement that's happening right on the Earth's crust here. But there are different types of seismic waves. There are actually 3 different types of wave here. And so they're listed here on my left. And you can see them listed as longitudinal waves, transverse waves, and up and down waves. So we're going to go deeper into depth on each of these waves here. And I also have included a short little visual for you guys to see how the waves move, because it just doesn't do it justice to describe them. It's better to actually be able to physically see them. Okay, so the first type of wave here that I'm going to be talking about is our longitudinal waves. These are also known as compressional waves. They're also known as a P wave or a primary wave. So these compressional waves is the best to think of kind of as a slinky. And I wish I had a slinky here to show you, but if you think of how a slinky moves, if you pull or push a slinky, you can see the wave move along the coil. And this is the P waves are the fastest of the waves, and they move through surface rocks and the solid or liquid materials below the surface rocks. And so in this particular image here, you can see the longitudinal wave. You can see where the compression is happening, and the energy is moving to the right in this particular case here. And the media is moving to the left and the right. So whatever you would see like on Earth's surface here. And I have an example of what a P wave would look like here in this video. So you can see it kind of moving. And if you imagine a slinky, it's moving from, in this case, from left to right. That's the direction. And this is our first primary wave. So we'll let it run one more time. All right, so that gives you a good idea of what a P wave would look like if you can imagine it occurring on Earth's surface and just below. Okay, so we also have our transverse waves. So these are also known as shear waves, also known as an S wave or a secondary wave. And so these are the second fastest of waves, and they do not move through liquid. And so this is what you would kind of see moving up and down where there is a crest or a top of the wave that's occurring. And so when you would have, say, an earthquake, you'd have the P wave come through first, or the primary wave, and then you would have the secondary wave come through. And so they're not as fast, so that's why they're coming through secondarily, and they're not moving through liquid. And so I also have an image here of your S wave, so you can see how that moves through a medium as well. So you can see this is more of an up and down motion. So kind of like if you flapped out a towel. So that's a good, I guess, real world example where the wave would move through, down, and across the medium, up and down, and then move in the direction of propagation. So in this case, it's moving from left to right. You can see it where it has the crest. I'll let that run one more time. All right, so imagine the P wave happening first, so that compression wave, and then imagine the shear wave following behind. All right, so we talked about P waves and S waves, or our primary and secondary waves, or our longitudinal and transverse waves, whatever you want to call them, but just keep those in mind that there's several different names for these waves, so if you have a question on the quiz, this is what they are referring to. So in Earth's interior, there are also up and down waves, also known as crest and trough waves. So these are a type of surface wave, and they are the slowest wave. And there are two types of these up and down surface waves here. And so they include the love wave, which is a horizontal S wave that will move from side to side. And there's also what we would call a Rayleigh wave, which is like a rolling water wave, kind of like a more destructive rolling water. I almost would think of this as like some sort of like barrel rolling down the hill, if you would imagine that underneath like a towel, I guess, as the surface. But and then your love wave would be kind of like a shaking sensation. So you can see the images here that I have provided. The wave direction for both of these types of up and down waves are moving from left to right. And you can see the love wave as, even though the wave is moving from left to right, it's still moving back and forth in that direction. And then the Rayleigh wave is kind of rolling along in that direction from left to right. And so you can see those two happening. And I have provided the same sort of interactive component here to show you what these waves would look like if they were actually happening. So remember, these are your surface waves. This is what you're going to be seeing right on the surface, these up and down waves here. Okay, so this is your love wave. So you can kind of see it's going back and forth. It's a little bit harder to see, but that black square on the top can kind of show you how it's moving back and forth. So the particle motion is going side to side, even though the direction of propagation is going from left to right. So I'll let this play once or twice more so you guys can see the movement of this particular love surface wave. All right, so hopefully you got an idea of the love wave. So let's move on to the Rayleigh wave. So remember, this is a rolling type style wave. And so you can see that black little box again can kind of show you how it's moving. It'll probably move in a more circular motion or a half circle motion, where it's kind of like a rolling sensation. So we're again moving from left to right for the direction of propagation. But you can see that blue arrow right here above me. So that's your particle motion. So it's kind of moving in a circle here, going this direction as it's moving along. And this is one of the most damaging types of waves that we will see, is this Rayleigh wave, this Rayleigh surface wave. And so I'll let it play once or twice more so you guys can watch it work and how it might respond. All right, so that's your Rayleigh wave. Okay, so let's move on. And these are your 3 different types of seismic waves that we just discussed. So these are your P waves, your S waves, and your surface wave. So remember, your P wave is your compression wave, your primary wave. So this is what you'll see, kind of like your slinky motion. Then we have our S waves. So this is the slower and stronger of the waves. This is going to come second after the P wave, and this is going to be moving up and down, kind of in an up and down motion. And then we have our surface waves. So we have those 2 types. Remember, the Love and the Rayleigh. So the Love is back and forth, and then the Rayleigh is kind of a circular motion. And so these are the 3 types of seismic waves that are referenced in your book, and that will potentially be on your quiz as well. So the Rayleigh is your more damaging of the 2 surface waves. Okay, so let's start breaking into different parts of Earth itself. So if we look at the Earth, if we took a cross section of it, this is what we might find here above me. And so the first part of Earth that we're going to talk about is the crust. Now, the crust is basically a thin layer of rock that covers the entire Earth. So this is the part that we are the most familiar with, that we see and interact with on a daily basis. If you walk outside in your front yard, you are walking along the crust. So it is pretty thin. It's between 0 to 100 kilometers thick. And there are differences in different types of crust. So we have 2 different types of crust, essentially. We have the continental crust and the oceanic crust, right? So in this image above me, you can see both parts of the crust, the ocean on the left and the continental crust on the right, or the mountains here. And so this is just to note that there are differences in both of those types of crust. So the oceanic crust is much thinner than the continental crust, and likely because it's been compressed by all of the weight of water over time. And then also seismic waves move through the oceanic crust faster than they do through the continental crust. So when you have waves that are moving through, it's moving faster through the ocean. And when you have instances of seismic waves moving through oceanic crust, this is when you get tsunamis happening. Whereas if you have seismic waves moving through the continental crust, you have earthquakes. So one thing to mention here is we have the Moravisic discontinuity, also known as the MOHO, and this is basically the boundary between the crust and the mantle. So we haven't talked about the mantle yet, but we will in a second here. And so this boundary is marked by an increase in velocity of seismic waves. And so seismic waves move differently through the mantle and through the crust. And so this discontinuity is the area where the change in seismic wave velocity is occurring. Okay, so we also have the mantle. I just mentioned the mantle, but what the mantle actually is it is the middle part of Earth's interior. So you can see it here in the image above me. It looks like it's kind of the yellowish area, yellow and the orange area. But the mantle is basically a thick shell between the core and the crust. And so this is taking up approximately 80% of the total volume of Earth itself. So how do we know what the mantle actually is? Well, there are three pieces of evidence that we have to determine what the mantle is. So the first piece of evidence is the study of seismological data. So scientists who have studied this data have determined, okay, this is, based on what we know, this is what the mantle is. But also studies of the nature of meteorites. So if we have any sort of meteorites that fall to Earth, when we're looking at meteorites, we can kind of get an idea of what the mantle is. And then lastly, there have been studies on material from the mantle that have been ejected from Earth via volcanoes. So volcanoes do eject materials within the mantle when they erupt. And so studying that helps us determine what the mantle actually is. And so the mantle is composed predominantly of olivine, which is a really pretty green mineral that occurs. If you've ever seen it in person, it's really a pretty mineral. But that's what the mantle is predominantly composed of. And so this is just showing you what the crust densities are relatively based on the continental crust, the oceanic crust. And you can even see the mantle here, the mantle right below the crust in that orange area. You can see the continental crust in the pink or tan, I guess, and then the oceanic crust in the darker coloration. You can see the ocean in the blue. So you have the oceanic crust, the continental crust. So you can see that this little, I guess, weigh scale here above me is showing you that the oceanic crust is much denser than the continental crust. And so this is just basically, this image is just showing you that the density of oceanic crust is more than that of the continental crust. So I mentioned the word the core before. So the core is what we would know as the very center part of the Earth. Now the core itself has two components. So if you look at the core, it has a liquid outer core and also a solid inner core. And so if you have an earthquake that's happening, and so I've listed two images here above me. If you have an earthquake that's happening, the seismic waves impact the core differently. And so if an earthquake is occurring, in this image you can see the earthquake is occurring where the star or the red area is. So that's the epicenter of your earthquake. Different seismic waves travel through the core differently. And so if you have a P wave happening, we have what we would call a P wave shadow zone, or this is a region that does not receive P waves. So the way that these seismic P waves are traveling through the core, they create what we would call a shadow zone where there is an area that is not impacted by these P waves. And this also happens with our S waves or our secondary waves. We have a secondary wave shadow zone if we have an earthquake happening. So our secondary waves, remember, they don't travel through liquid. And so that particular wave, the S wave, does not receive, it has a bigger shadow zone that does not receive S waves because that outer core is preventing those S waves from traveling through it. Whereas the P waves, the primary waves, can travel through some liquid and outer areas of hard, solid areas of rock. And so P waves can go through the core, S waves cannot go through the core, and so we have those shadow zones that occur as a result. So more on the core. So remember, the core is the center part of Earth. And then we do get evidence from meteorites that indicate that Earth's core is made up of mostly iron. And so if I had a chart, which I should have included but I didn't, of what Earth is primarily composed of, it would show you that the core makes up 15% of Earth's total volume, and that the core itself is mostly made of iron. So we might have maybe 15 or less than or greater than percent of iron composed primarily of the Earth. And so we can kind of determine what the core is made of due to our meteorites, right? So when we have meteorites that fall to Earth, scientists can examine those, and there are two types of meteorites that will fall to Earth. So the first kind are stony meteorites that are primarily made of silicate minerals. And the second kind is iron meteorites. They're made up of either iron or iron-nickel alloy. And so based on this information, we can determine that our Earth is composed of silicates and possibly iron in the core. And so this is showing us a more detailed structure of Earth. So this, I've used this image before, but I'm including it again here. Because it does show us the asthenosphere and the lithosphere. So these are two terms that are important. So let's cover each of them. So we have the asthenosphere. So this is our reddish orangey area in this image above me here that you can see. So another name for the asthenosphere, or what it actually means, is weak shell. And so the reason that it's named weak shell is because it is what we would consider a hot, elastic, semi-liquid layer. And this layer goes around the entire Earth, so it wraps around the whole Earth. And it is a low velocity zone. And so that's our asthenosphere. And then we also have the lithosphere. So our lithosphere is what we would call our stone shells. That's what our lithosphere means. So this includes the crust, the moho, and the upper mantle. So this is including the crust, which is what we are familiar with. So that's our lithosphere. And in this image here, you can see the lithosphere is pretty much the uppermost solid part of the mantle you can see, which is that very beige zone, and then also the crust itself. So here you can see I've just included some more information on the lithosphere. So the lithosphere is what we would know as the land itself. I mentioned it was the crust and the uppermost part of the mantle. So basically, Earth was a ball of molten matter approximately 4 billion years ago, but over time it cooled enough to allow differentiation to occur. And so that is how the Earth itself created these different layers as it cooled. So the core is the most dense part of Earth that contains all of the iron. And so the mantle was also created when the Earth cooled 4 billion years ago, and convection occurs in this particular region of Earth. And then lastly, crust, which is what we're all familiar with, which is part of the lithosphere. The mantle and the crust is part of the lithosphere. Only the uppermost part of the mantle, though. But the crust we know does move because we're on it, and we know earthquakes are happening, we know tsunamis are happening due to movement of the oceanic crust. We know that there is movement over time, very slow, very fast movement, depending on what's happening with our plate tectonics. So we know the crust is moving. And so this is what we're going to cover in our next lecture. We're going to talk all about plate tectonics and earth crust movement and all of the different waves that can occur and create different types of earthquake and all that fun stuff. So this is my last slide that I have for you. Here's an image that I've included up above of the inner core, the outer core, the mantle, and the crust, basically what was created as earth cooled. So this is all that I have for you guys for today's lecture. I'm going to try to get the other lectures out today and make sure that they're available for you guys to watch at your leisure. But next week we're going to be covering plate tectonics, and we're going to try to get through Module 11 and Module 12 all in this week. So bear with me and turn in all of your assignments, and hopefully you'll be hearing from me soon.